Learners, today we'll see how to conduct a transient analysis in RL, RC and RLC circuits. For that, we need to take the inputs before going to this transient analysis. So this transient analysis is occurred when a source is directly connected to the load. So whenever you suddenly turn on the switch at t is equal to 0, so because of the presence of this inductor, so the current in the circuit may not start instantaneously. So if I assume this is the voltage V and this is resistance R, inductance L, so here, if you observe here, the basic property of an inductor. So inductor, if you it opposes sudden changes in current. So what happens? For every sudden change in current, inductor acts as open circuit, and gradually after some duration of time it becomes short circuit. So based upon this information, let us assume that at t is equal to 0, so the switch has been closed. So whenever the switch has been closed, a voltage of v volts is directly applied to the RL load. So this RL load, because the L, it doesn't allow sudden changes in current, so it opposes. So therefore the circuit is modified as, so the inductor acts as open circuit. So after closing the switch, so the inductor acts as open circuit. So after that, so the total voltage across these terminals is nothing but your supply voltage. After gradual time, so after some duration of time, so the inductor gradually changes and it becomes as short circuit. So therefore at that time the voltage is equal to 0. In previous condition, voltage is equal to supply voltage across inductor. So if you assume the graph, this is the graph. So if I assume this is the voltage or current magnitude with respect to time. So this uh, this indicates your supply voltage Vs, and then so this is the inductor voltage. Initially it has an voltage. Why? Because it acts as open circuited, so suddenly it increases to grids supply voltage, and then it gradually decreases and reaches to 0 after some duration of time. Whereas current, so initially the inductor acts as open circuit, so whenever it is open circuit, the current flowing through the circuit becomes 0. So which means that the current starts at 0 and it gradually increases and reaches to the maximum value. So as it is short circuit, so the maximum value of current I is equal to V by R. So V by R, so what is the value of resistance? That divided by Q gives the value of inductance. So current. So this is the graph for an RL circuit. Similarly, if we observe for RC circuit, so let us consider an RC circuit. So first you need to know the behavior of RC circuit or C element with respect to changes in voltages or current. Let us assume the switch is closed at t is equal to 0. So therefore, the current flowing through the circuit will be, so the initial conditions of capacitor is, capacitor doesn't allow sudden changes in voltage. So if there is any voltage disturbance, automatically it acts as short circuit. So short circuit, which means the voltage across the terminals is 0. After that, it gradually increases. After certain duration of time, it acts as open circuit. V is equal to the supply voltage Vs. So this is Vs, and then this is your voltage, load voltage. So based upon these characteristics of capacitance, now we'll see the graph here. So this is the graph. So this is time, and then supply voltage Vs, and then voltage across capacitor. Vs will remain constant. So voltage across capacitor, initially it is zero. Why? Because initially it acts as open circuit. So initially it is zero and it gradually increases and reaches to the supply voltage. But whereas the current, so under short circuit, current I is equal to maximum. So therefore, the current will be maximum, and then it gradually decreases equal to zero, and it gradually becomes zero. So these are the expected graphs for an RL and RC circuit. So now we'll see how to simulate these RL and RC circuits in PSpice software. We clear? So for that I need to open PSpice software. So here I have Capture CIS. So before that, so as I need to study the transient behavior, I cannot apply a DC voltage source directly. I am applying a piecewise linear voltage source PWL in PSpice. So where what are the time, so let us assume that I am taking a DC voltage. So this is the DC voltage. At every time instant I need to specify the magnitude of the voltage. So the input for VWL is time. So time T1, T2, T3, T4, so on, and then voltage, respective voltage magnitude. So what is this? So that is V1, V2, V3, V4, so on. So first I need to apply the time. So if you observe here, at t is equal to 0, the magnitude also 0. So therefore for the first condition I'll write t1 is equal to 0, v1 is equal to 0. Similarly, t2 is equal to 0. So the second instant at the same time t is equal to 0, it has been increased to some, let us say, 5 volts. So v t2 is equal to 0, v2 is equal to 5. So if I take 0, so it won't accept. So instead of taking 0, I'll take 1 nanosecond. 1 nanosecond. For this 1 nanosecond, the voltage has been increased from 0 to 5 volts. After that, t is equal to 1 millisecond. V3 is equal to T3 is equal to 1. V3 is equal to 5 volts. Next, T4 is equal to 2 milliseconds. V4 is equal to 5 volts. So which means that I have, so for every time, so the magnitude of voltage has remained constant. So therefore I am, so therefore in the piecewise linear matrix, I write in place of time t1 0, and then 1 nanosecond, and then 1 millisecond, and then 2 millisecond, 3 millisecond, and then respective voltages at t is equal to 0 0, it is 5 volts, 5 volts, 5 volts, and then 5 volts. So which means that if you observe here, this will be a DC waveform or a step waveform which has constant magnitude. Now to analyze the to analyze the behavior of RL and RC in DC circuits, I am assuming a piecewise linear waveform, and I need to give the conditions like this. So we'll check how to give the conditions and how to check the responses. So for that, I need to open PSpice software. In PSpice software, I am taking new project file, new project. So it is transient analysis. I'll type it as transient transient RL. Similarly, I can do it for transient RC. Click on OK, and then click on create blank project. Click on OK. So now the window has opened. I need to search for the parts. So which first part I need? Piecewise linear. So that part is available in sources. If you go to sources, uh, sources, if you scroll down for the OS, so you have vpwl, which is nothing but v piecewise linear, where I can define that magnitude of the waveform at each and every time interval. So I can give any waveform by using this piecewise linear. So I'm taking this piecewise linear waveform, sorry, piecewise linear component, and I'm placing it, and I require r. So element R, so I need to go for analog, and I need to search for R, resistance. So one resistance. Similarly, I need to connect it for inductance. So inductance R L. So this is inductance. So I'm rotating the inductance, and then I'm placing the inductance here. So this is our circuit diagram. Now I need to connect the elements. So from V1, I'm connecting it to R1. From R1, I'm connecting it to L1. From L1, I'm connecting it to V1. So this completes the circuit, and I need to place ground terminal. So this is the ground, zero source. I'm clicking on it. So this is my circuit. First, I'll take the value of R is equal to 1 ohm, and then L is equal to 10 millihenry, so 10 microhenry. And then now I need to give the time and magnitudes of V1. So double click this piecewise linear, and if you slide this bar, at last you have the magnitudes. What is T1? T1 is equal to 0, V1 is equal to 0. At T2 we have taken it as 1 nanosecond, and the magnitude has changed from 0 to 5, and then 1 millisecond, the magnitude is 5, and then 2 millisecond, the magnitude is 5, and 3 millisecond, the magnitude is 5, 4 millisecond, the magnitude is 5. So you can stop if you want, otherwise you can fill it. 6 milliseconds, sorry, I think 5 milliseconds. So the magnitude is 5, and then 6 milliseconds, the magnitude is 5. So what I have done, I have designed a waveform, a step waveform, which has a magnitude of 5 volts, and I am giving the timings, and then close this. So now I have given the input waveform, and the values of R and L. Now I need to simulate this. So here, PSpice new simulation profile. So I am taking the name new simulation profile, and then create. Here it comes the major part. Here you need to take. So if you observe here, DC time domain in transient analysis also can be done the same. Here I need to run time. So how many milliseconds I have given? So I'll take 6 milliseconds. 6 milliseconds is the time voltage V1 magnitude I have given. I need to run it for 6 milliseconds. If you observe, and then click on run. So if you click on run, so a blank window will be opened. Now I need to measure the current as well as voltage. So first take the value of current flowing through the circuit, IR1. So the current is this. If you observe here, you cannot clearly see what is the time taken by the waveform to reach its maximum value. So that's why I'll take the time as zero point 0.5 milliseconds, so that the waveform, you can clearly observe the waveform. So again, I am going to PSpice edit simulation profile. So, and then I'll write it as zero point 0.5 milliseconds. and then I'll run this file again for zero point 0.5 millisecond. So click on OK. Then you'll get the waveform, sorry, window, and then I of R1. Now, if you observe, you can clearly observe the magnitude of your waveform. So, the value in the current is initially it is zero and it is gradually increased to its maximum value. Now, if you observe, similarly, I need to observe the voltage across the inductor. As we have discussed, voltage inductor initially acts as open circuit and finally it acts as short circuit. So I need to say whether it is following the same. If I click on OK, if you observe here at t is equal to 0, whenever you are turning, whenever the signal is applied, so it acts as open circuit. Suddenly the voltage reaches to the supply voltage. If you observe here, this is 5 volts. Suddenly the voltage reaches to 5 volts, and then it gradually starts decreasing, and after some duration of time it becomes 0. So this is the transient analysis in case of RL circuit. So here we can take what happens if resistance increases. Is it clear? So that also we can see. So for that I need to get two more circuits. So first I'm considering the same circuit here. I'm just copying the circuit and then placing it aside. I'll take three uh, circuits of same type, same RL circuit. Now I'll observe what is the effect of resistance. So in the first circuit, so R1 is equal to 10. In the second circuit, I'll take R1 is equal to 5 ohms, and then and here in this case I'll take R is equal to 10. So you need to keep in mind while you are running the simulation, the variables should have different name. So I cannot keep V1 again V1 again V1. So I need to change the name here. Double click on that. So I need to change V2 and then V3. So click on OK. So if you have same name for the different resistances, it will show. So repeated resistances are there. So I need to take it as R2 and then R3 and then L2 and then L3. So where I have changed. So no element is common in these three circuits. Now, what is the only difference I have taken? Instead of giving the value of resistance R1, I am considering 1 ohm at a time, 5 ohm, 10 ohm. Now we'll observe what happens to the current and what happens to the voltage magnitudes here, and what is the time taken by the waveform to reach its maximum value. Is it clear? Now again I'll run the same waveform, same circuit. So again I'll get the output waveform. So if you observe here, now I am very curious about checking the currents of R1, R2 and then R3. So click on OK. So if you observe here, R1 is of 1 ohm, R2 is of 5 ohms, R3 is of 10 ohms. If you observe the graph, so here we have a different graph. So if you click on the graph and right click properties, you can change the width of your waveform such that it is clearly visible for us. So I am taking the second waveform properties, I am increasing the width, click on OK. And then similarly the third waveform properties and then width, so which makes us clear to see what is. So what happens if the resistance increases, and if you observe the time duration, so the time duration of this particular is about 40 microseconds, whereas it reaches to the same value within small duration of time. So this is the transient. Now similarly I need to observe the voltages across the inductors. So for that I am taking V So V1 of L1, V2 of L2, and then V3 of L3. Three waveforms I need to take. V2, or I can say take it as V of 3 2. So if I take this, so the first resistance has maximum voltage, and then after that the gradually decreases. Let us see it individually. So first I'll trace for V of L1. So V1 of L1. So this is your magnitude. Similarly, V1 of L2, V1 of L2. So if you observe the peak, so or you can directly add all the three values. So add trace. So V1 of L1, V1 of L1, L2, and then L3. So if you observe these graphs, again I'll change the characteristics of this. I'll take width as more, say first one, second one, third one. So I am changing the width. So for our, I am changing the color also. So I'll take near yellow color. So if you observe here, the duration, the time taken to reach the zero value is gradually decreasing as the value of resistance increasing. So that you need to observe. So for different values, similarly, you can do it for different values of inductances. Is it clear? So this is how you need to observe the transient. So transient is nothing but whenever you are applying a sudden voltage or current to a circuit. So what is the behavior of the current? So how the current behaves? Whether it gradually suddenly increases or it takes some time because of the presence of L and C. So this is about RL circuit. Now similarly we can see it for RC. So for that, I am taking the new file, new project. So transient RC. So click on OK, create blank project. So I am taking the new project and following the same procedure, taking the R and L, sorry, C, resistance, next capacitance, and then piecewise linear waveform, piecewise linear source. So I need to go for source, and then I need to say VPWL. So VPWL. Click on OK, and so connect all the elements. So from R1 to C1, from C1 back to the supply, and I need to connect the ground terminal. So ground. So this completes. Now I'll take the same values of resistance 1 and then capacitance as 10 micro. So micro you can represent it as UF, microfarad. Okay. So again, the waveform I need to take the values of different time instants. So T1 0, T2 1 nanosecond. So next 1 millisecond, 2 millisecond, 3 millisecond. So you can give if you want up to 6 milliseconds, otherwise you can complete it. So here if I take it as 5 volts, 5, 5, T5, 5. So how many time instants I have taken, those many voltages I need to take. I cannot take T1, T2, T3, T4. We cannot give it as V1, V2, V3. You cannot leave the remaining columns as empty. So it will get an error. So you need to completely give the values for the given time intervals. Now again, I'll run the program for that PSpice new simulation profile. So how many times I think we have taken for 3 milliseconds. So here in transient analysis, I need to change the runtime from 3 milliseconds and then apply, click on OK and then run the program. So if you run the program, you'll get this window, waveform window. Here I can represent I of R. So if you observe here, what happens? Initially, the current has been increased to a maximum value as the capacitor acts as short circuit, and then it gradually decreases and becomes zero. And when it comes to voltage across C1, so if you observe here, initially the voltage is zero and it gradually increases and matches to your supply voltage. So I can change the width of my waveform for your clear visibility. Similarly here, current waveform. So properties, you can check. So this is the wave. So where you get exactly. So reverse to that of capacitance. In capacitance, the red color indicates current. This indicates voltage. Here it indicates current, green color, IR1, and then what red color indicates VC1. If you observe it here at the bottom of the graph, you observe what are the waveforms that you are taken, color, and then its variable. So across which.